Assalamualaikum, my name is Farzana Ishantisa. My matrix ID is 083175. Our group consists of 5 members, which is Kalisa Liana binti Khairul Nizam, Siti Nur Aini Sofia binti Siddiq, Nur Harisha Mizan binti Muhammad Mazli, Nur Fitri Huda binti M. Yusuf, and Roshan anak lelaki Sivanisan. Okay, modern distributed systems store data across multiple nodes to improve scalability, availability, and fault tolerance. But distribution introduced challenge in naming, which is how resources are allocated, and replication consistency, how data stays correct across nodes. Different naming schemes and consistency models impact system performance in different ways. So the goal of this project is to evaluate how flat, structured, and attribute-based naming perform under eventual as sequential consistency using concurrent client simulations. Some of the performance metrics mentioned in this report is response time, throughput, and inconsistency rate.
In this presentation, I will explain a distributed system simulation that compares different naming schemes under two consistency models, which is sequential consistency and eventual consistency. This project simulates a distributed system where data is stored across multiple nodes and accessed by many clients at the same time. The goal is to compare how different consistency models and naming schemes affect system performance. So, we measure this using performance metrics such as response time, throughput, and inconsistency. In simple terms, we are studying how fast, scalable, and reliable the system is under different configurations. The simulation compares two consistency models, which are sequential consistency and eventual consistency. So, for sequential consistency, it ensures all nodes are updated before any reads occurs. This guarantees strong consistency but results in slower performance. Eventual consistency allows faster writes by updating only one node first, while other nodes are updated later. This will improve speed but may cause tail reads. For naming schemes, flat naming has the lowest overhead, structured naming simulates direct tree traversal, and attribute-based naming simulates metadata search, making it the most expensive. To evaluate performance, we measure three key metrics, which are average response time, throughput, and inconsistency rate. So, for average response time, it shows how long each operation takes. Throughput shows how many operations the system can handle per second. Inconsistency rate measures how often tail reads occur. So we compare these metrics across different consistency models, naming schemes, and system loads to understand trade-off between performance and consistency. The simulation consists of 5 main classes, which are main simulation, storage, name resolver, client thread, and metrics. So for the main simulation, it acts as the experiment controller. It runs multiple tests by varying the number of threads and nodes. And for the storage class, it represents distributed storage replicas and handles both sequential and eventual consistency writes. For the name resolver, it simulates the cost of different naming schemes such as flat, structured, and attribute-based naming. Each client thread represents a user request that performs name resolution, writes data, reads data, and checks for inconsistencies. Finally, the metric class collects and calculates performance results like response time and throughput.
After all client threads complete their execution, the simulation aggregates performance metrics collected during runtime. First, average response time is calculated by dividing the total response time by the total number of operations. This metric represents system latency, indicating how long on average a client operation takes to complete. Next, throughput. Throughput is calculated as the total number of operations divided by the test durations in seconds. Throughput measures the system capacity and shows how many operations the system can handle per second under a given workload. Finally, the inconsistency rate is computed as the percentage of stale reads out of all read operations. This metric reflects data freshness and highlights the impact of eventual consistency, where replicas may temporarily hold outdated data. These metrics are printed for each naming scheme and consistency model, allowing direct comparison of performance and consistency trade-offs. The output displays results for each naming scheme, including flat, structured, and attribute-based naming. For each scheme, the simulation reports the average response time in nanoseconds, the throughput in operations per second, and the inconsistency rate as the percentage. By comparing these values, we can observe that lower response time and higher throughput indicate better performance, while a higher inconsistency rate indicates weaker consistency guarantees. In conclusion, this simulation demonstrates real-world distributed system behavior. Strong consistency provides correctness but reduces performance. Eventual consistency improves speed and scalability but allows temporary inconsistencies. Naming schemes also play a significant role, with attribute-based naming having the highest cost. Overall, the project highlights the trade-offs system designers must consider when building scalable distributed systems.
This slide shows the overall architecture of our distributed system. Although the system runs on a single machine, it is designed to behave like a real distributed environment. The system consists of clients, a naming service, storage nodes, and a simulated network layer. All components communicate using message passing, which allows us to study scalability and consistency in a controlled setup. Here, we show the main process roles in the system. The client represents users and sends read and write requests. The naming service resolves logical names into physical node identifiers. The storage system is divided into a primary node, which handles all write operations, and replica nodes, which serve read requests and receive replicated updates. This slide explains how components communicate. The system uses asynchronous message passing, meaning processes do not communicate directly or share memory. Messages are sent through a network router that introduces artificial delays to simulate real network latency. This approach allows us to observe how distributed systems behave under concurrent requests and delays. This slide explains the naming strategies used in our system. Flat naming provides fast lookup but does not scale well. Structured naming uses a hierarchical format which increases lookup time but improves organization. Attribute-based naming allows clients to locate services based on properties, making it flexible for dynamic systems but more expensive in terms of resolution time.
Data replication and consistency model. To ensure data availability, our system replicates information across multiple storage nodes. Each item carries a version number that updates with every write operation. We support two consistency models. First, sequential consistency. Here, the primary nodes waits until all replicas confirm the update before responding to the client. This guarantees a strong consistency, but it also increases write latency. Second, eventual consistency. In this model, the primary nodes respond immediately after updating its local copy. Replication happens asynchronously, which improves performance but may result in stale reads. Clients detect stale data by comparing version numbers with those they have seen before. Next is process and thread model. To simulate distributed system behavior, we use a multi-threaded architecture. Each logical component consists of clients, primary nodes, and replicas, run in its own thread. This design allows parallel execution, meaning components can operate independently and concurrently. It also makes experimentation easier since we can introduce delays or fault at the thread level. The model preserves three essential properties: concurrency, where multiple operations run simultaneously; isolation, where each thread maintains its own state; and scalability, where new components can be added simply by spawning more threads. Next, fault and failure simulation. To test system robustness, we introduce control faults that limit real-world conditions. These include delay message delivery, drop replication message, and slow replica behavior. Such scenarios are critical for evaluating how consistency models respond under stress. For example, under sequential consistency, delay acknowledgement and can block client response, increasing latency. Under eventual consistency, faults may cause longer periods of state data. This simulation helps us analyze the trade-off between consistency, availability, and performance when failures occur. Next, scalability considerations. Scalability is assessed by increasing system load and complexity. We add more client threads to simulate higher concurrency, more replica nodes to measure replication overhead, and expand naming strategies to test service discovery at scale. These tests reveal architectural limits. Sequential consistency often struggles with large replication counts due to synchronous coordination. Eventual consistency scales better, but at the cost of more stale reads. This result guides us in making informed trade-off for real-world deployment. Evaluation metrics. Finally, we measure system performance using key metrics. These include request latency for PUT and GET operations, naming lookup time, and the number of stale reads and the stale read rate. By analyzing this metric across different fault scenarios and scalability levels, we can clearly see the trade-off. Sequential consistency reduces stale reads but increased latency. Eventual consistency
delivers faster response but tolerates temporary inconsistency. This evaluation helps us decide which consistency model best fits specific application requirements.
This graph compares throughput as the number of nodes increases under eventual and sequential consistency. As nodes count increases, throughput decreases due to replication and coordination overhead. However, eventual consistency scales better because write are done locally and replicate asynchronously. In contrast, sequential consistency requires global ordering, causing throughput to drop much faster and nodes increases. This graph showed how eventual consistency behaves under high concurrency. When the number of threads increase, stale rates also increase due to replication delay. Among naming schemes, flat naming has the lowest inconsistency because lookups are simple and faster. Structured naming is moderate, while attribute-based naming causes the highest inconsistency due to complex resolution. Here we observe throughput under sequential consistency as thread count increases. Throughput increase initially due to better CPU usage but slows down at higher threads count. This happens because threads global ordering creates contention. Flat naming performs best, while attribute-based naming performs worse due to highest coordination costs. This graph shows response time under sequential consistency. As concurrency increases, response time also increases because threads compete for synchronization. Flat naming has the lowest latency, while attribute-based naming has the highest due to complex lookup and ordering. Overall, eventual consistency with flat naming is the best model. It maintains high throughput, scales well with nodes and threads, and keeps latency low. Although temporary inconsistency may occur, it provides the best balance between scalability, performance, and reliability, making it suitable for large-scale systems such as cloud storage, caching, and social media platforms.
To conclude our findings, our results show that different naming schemes and consistency models have clear trade-offs depending on performance needs. Sequential consistency gives a strong correctness, but it significantly slows the system down as more threads and nodes are added. In contrast, eventual consistency scales much better, allowing higher throughput and lower response time, although it can temporarily produce stale data. Among the naming schemes, flat naming consistently performs best because it has the lowest lookup cost and minimizes inconsistency. Structured naming is more organized but adds overhead, while attribute-based naming is the most flexible, yet suffers from the high latency and stale read rates. Overall, the best balance comes from using eventual consistency with flat naming, which is this combination provides strong scalability and performance while keeping inconsistency at an acceptable level. This makes it the most practical choice for large and dynamic distributed systems such as cloud service or caching platforms.